Hello, my name is Omari Hitson, and thank you for watching my Lab 3 report entitled Determining the Unknown Mass of a Black Hole. During this presentation, I intend on providing an explanation of the lab goals, its purpose, and why the answer to the upcoming questions are of importance to the scientific community. Following this, I will detail the fundamental principles discussed in this lab and the assumptions necessary to perform and apply these principles. I will then provide an overview of the code used to complete my final answer, present this final solution, then state the analysis of my findings. In this lab, I was provided the mass and trajectory of a star orbiting a black hole of unknown mass. Using the mass of the star, 2 times 10 to the 30th kilograms, and the randomly generated trajectory shown on the right, I will utilize several of Newton's fundamental principles to deduce the mass of the black hole observed over the duration of one Earth day. During this one Earth day, the star and black hole both act as a system, and we utilize Newton's laws of gravitation to deduce information about one of the objects in this system. The purpose of this deduction is to answer two basic questions. 1. How do the perpendicular and parallel force components compare to the rate of change in momentum perpendicular and parallel components? 2. If under the same circumstances, including the same trajectory, same star mass, and assumptions, the black hole mass was changed, would we be able to calculate that new unknown mass? This knowledge is particularly helpful and relates directly to one of Newton's principles that I will soon discuss. Sometimes we're able to observe the effects of a particular circumstance, but unable to directly observe its causes. Utilizing the methods outlined in this lab, the scientific community is better able to observe the nature of unseen bodies in the universe, like the black hole shown to the right. To conduct this experiment, we will utilize a derivation of Newton's second law that states the force applied to some object, the cause, is equal to the change in momentum observed after the event, the effect. In our case, the force of gravity between our two celestial bodies is the cause, and the star's change in momentum along its trajectory is the effect. We also utilize Newton's law of gravitation, which explains that two objects will attract each other with a force that is directly proportional to the masses and indirectly proportional to the square of their distance from each other. The equation we will use to illustrate this is shown below. More on this equation as we progress through the investigation. Our investigation relies on several stated values and a few assumptions. Firstly, we know that the mass of the star is 2 times 10 to the 30th kilograms. Next, we know that the black hole is located at the origin 0, 0, 0. We are able to deduce the location of the star utilizing Newton's second law to predict the position along the randomly assigned trajectory of the star. Thus, we know the location of the star. We are also given that the net force acting on the planet by the black hole is contributed solely due to gravity. Finally, we know that the duration of the observation is one Earth day, or 86,400 seconds. Rearranging Newton's law of gravitation, we are given the equation that we will use to deduce the mass of the black hole. In other words, the mass of the black hole is equal to the net force times the radius squared over the g constant times the mass of the star. The radius component is given by the star's position minus the position of the black hole, whose vector is 0, 0, 0. Thus, in the equation, we remove the black hole position and represent the radius as the magnitude of the star's position. The mass of the star is stated in the problem as 2 times 10 to the 30th kilograms, and g is representative of the gravitational constant 6.7 times 10 to the negative 11. This leaves only the net force portion of the equation. We know that in our assumptions, the net force is equivalent to the force of gravity. However, in order to compute this, we would need to know the mass of the black hole. So instead, we utilize Newton's second law, and we know that the cause is equal to the observed effect. So, we supplement the force component with the planet's change in momentum, equal to the change in momentum of the parallel component plus that of the perpendicular component. Utilizing the velocity of the star and the mass of the star, we can then calculate the momentum, both in the parallel and perpendicular components. We can see here in the code where we have supplemented F net for the change in momentum over the change in time. Piecing all of this together, we arrive at our aforestated equation for calculating the unknown mass and arrive at the answer 1.7033 times 10 to the 34th kilograms. So we return to our initial questions. How does the perpendicular and parallel force components compare to the rate of change of the perpendicular and parallel momentum components? As we distinguished before, the force components represent the cause of some later effect. F net parallel is equal to the force applied parallel to the object's momentum. The F net perpendicular is representative of the force applied perpendicular to the object's momentum, while change in momentum in the parallel component is representative of the object speeding up or slowing down, and a change in momentum in the perpendicular component is representative of the object changing direction. Finally, we come to our last question. Under the same conditions, trajectory, and assumptions, could we calculate the mass of a new unknown mass black hole located at the origin of our system? The answer is no, we cannot. Looking back at Newton's gravitation equation, we see that the force of gravity is calculated using the radius, g constant, and two masses. If a new mass was supplemented, the force of gravity would change. However, the question states that the trajectory remains the same, so it would be impossible to calculate this new mass, as the force would also have to stay the same in this circumstance. That concludes my Lab 3 report, determining the unknown mass of a black hole. Thank you for watching.